Welcome back. In this video we finish off the first chapter, which is meant as an introduction and as laying the foundations for calculus on one variable, by introducing complex numbers, which can be seen as an extension of the real numbers in some sense, which looks kind of scary in the first occurrence, but it's a thing of getting used to it. So they are really not that complicated. Once you get used to computing with them and to do computations with them, you will also get exercises on this. And we will now, in this section, I just want to introduce some basic things. I will go into detail a bit further on the complex numbers later on, but I need some prerequisites for to do reasonable things with them. But here we kind of see them for the first time, see what they are doing, what they are good for, and how to compute with them. And this we will then use frequently, because in many of the things to come, the proofs would basically be the same for real numbers and for complex numbers, and you can really just take, and I can really show you that you can do everything in the complex, or many things in the complex numbers directly, and don't need to focus on the real numbers, but yeah, it's just as fine with them, as you will see. And yeah. Okay, so one problem with the real numbers. Some simple equations in the real numbers have no solution in the real numbers. So the simplest of these is probably this equation. X squared is equal to minus 1. We have seen generally for ordered fields that squares of elements are always non-negative. So this cannot have a solution in an ordered field, so especially not in R. This is bad, because in general we want kind of, for computational reasons, we would like to extend our domains or to extend our numbers to some sense where we can solve all of these equations, and all equations which look similar to this. So yeah, precisely speaking, polynomial equations, as we will see later on. And as we will see in the end of the section, it's really the complex numbers who do this job, who have solutions to this equation and to many others. And this turns out to be very useful for computations. Also, if complex numbers are kind of hard to understand, so kind of from a intuitive, from a point of view like where they're occurring in nature or something, but it turns out that they are really useful for computing, and they're really useful in some formalism, like I think in quantum mechanics they appear a lot. And also sometimes there are kind of some real problems about real numbers, like computing very complicated integrals or something, which cannot be done by just standard methods in R, but they are tricks when you kind of use the complex numbers. You can really kind of find also real solutions to some very complicated problems of real numbers that would not be directly solvable by the standard methods. But this goes way beyond the scope of this lecture. So this thing is now a solution that equation that has no solution in R, and the idea is, so as I just mentioned, we define a bigger field, so bigger than the real numbers. Let's call it K, such that every such equation has a solution in K. Such equation is now, of course, not really precise. I will state later what I mean by this. Every such equation has a solution in K. Okay, and this field will be the field of complex numbers, which we will denote by C with this double dash or whatever this is called anyway, but with this symbol C with an additional bar, the complex numbers. Okay, and before kind of relating them to these things, I will just introduce them axiomatically, because you can really define explicitly some set with an addition and a multiplication, which becomes a field, and we will see how this works out next. So what we do is we define an addition and a multiplication on R2. So R2, so R squared, so pairs of real numbers. And we now define some rules of how to add and multiply them. First of all, by this I mean, of course, let me mention this here, operations which are called plus and dot, because these should then be the field operations from R2 times R2 into R2. So we take two elements of R2 and get one element back. And these should be defined by the following rules. If I take 2 points, x1, y1, and add this to some point x2, y2, I just do the component-wise addition, so like you would do in R2 as a vector space. X1 plus x2, y1 plus y2. More on vector spaces much later in this lecture. And the product now looks a bit awkward. Namely, it looks like this. We multiply x1, y1 with x2, y2 by having in the first component the product of the first entries, x1, x2. So this now, of course, multiplication in the real numbers. Here, of course, addition in the real numbers. But here, so we multiply the first two elements and subtract the product of the second element. So minus y1 times y2. This is the first entry. And the second entry as an element of R2 is just the mixed products, x1 times y2 plus x2 times y1. This looks mysterious upon first sight. But we will see later that this has really some nice properties for all x1, y1 and x2, y2 in R2. So, now to introduce the complex numbers, you maybe have already seen or heard something about complex numbers where there's this imaginary unit I. And what we now do is kind of to introduce different formalism, because it's actually not more than that. We have this addition here on R2, but we want to write the complex numbers differently, namely, so the formalism, we let C denote just as a set of all elements x plus I times y, where x comma y is in R2. So this is just basically a fancy way of writing R2, just not as this coordinate tuples, coordinate pairs, but by introducing this element I, where I is just some formal variable. So I is a formal variable, which so far doesn't have any meaning at all. Okay, and of course, what we get is, in the terms of maps, we get a bijection, so a one-to-one correspondence between this set C and the set R2. Namely, simply, we take this map, which should be the bijection phi, from C to R2, and define this phi by phi of x plus I y is just the pair x, y as an element of R2. Then this element, this is of course almost trivial to see that this is a bijection. Okay, and if we view kind of elements of C as points in R2, we can of course consider the same operations here, but this time write this as operations on C. So using this formalism of x and I, of these i's and writing them in this way. Then we can see addition, continue on the next blackboard. So we see addition and multiplication as maps plus dot from C times C to C. And now, just for completeness, I will write down these operations again, but this time using this formalism of complex numbers. So x1 plus I times y1 plus x2 plus I times y2. This would then be, if you just take a look at the definition and the way phi is given, this is just x1 plus x2 plus I times y1 plus y2. And the multiplication looks a bit different. x1 plus I y1 times x2 plus I y2. This is then given as x1 x2 minus y1 y2 plus I times x1 y2 plus x2 y1. Okay, this is simply just taking this, taking this to the different formalism. So this is not a new thing. And now this is, okay, yeah, for all, of course, for all x1 plus I y1, x2 plus I y2 in C. Okay, and now we come to this, the crucial property, and I again make a hybrid of definition and a theorem. This is 166. If we take C with plus and dot, so with this addition and this multiplication, this is indeed a field. Okay, and if it's a field, I want to give explicit formulas for the neutral elements and for the inverses of the two operations. So first of all, the neutral elements. If you see the way plus is defined, it's not really hard to tell how the neutral element will look like. Neutral element of plus. This is so 0 again written, but as a complex number in this way, it would be 0 plus I times 0, corresponding to the point 0, 0 in R2. And since this addition is defined component-wise, of course, nothing happens if we add this element. So this is a neutral element. The neutral element of the multiplication is the element 1, and 1 is now, if you write this again in this complex number way, this would be 1 plus I times 0. And then if you check the formula, I won't give the computational details here because this is something you really do yourself and you learn much more about complex numbers as if I would show it to you, that this is indeed a neutral element. This just follows basically from the formulas, from the formula of multiplication. This is something you can check. The inverses. So the additive inverse of x plus iy. This is something we are used to writing as minus x plus iy. This is explicitly, if you write this in formalism again, this would be just the number minus x plus I times minus y. These are real numbers. So this would, since we add component-wise, we have component-wise the additive inverses of the two components here of x and of y. So this is really an explicit formula for all x plus I, y, and c. Now the multiplicative inverse, this is a bit more complicated. This is x plus I, y, and to the minus 1. And recall we only have inverses for all non-zero elements. So for this element 0 plus I times 0, this doesn't have an inverse, but all others have. But we can assume that they are not both 0. And it turns out by some computation that this is, the inverse of this is x minus iy, minus iy, divided by the real number x squared plus y squared. And this is already shorthand notation, because if we write this again in the complex, in this really nice way of having something plus I times something, this would be x over x squared plus y squared minus or plus I times minus y over x squared plus y squared. So this is for all x plus iy in C star, so C without 0. Okay, this is non-obvious and we will check this, but yeah, now this was the theorem part, and now the definition part of this hybrid. This field, C plus dot, is called the field of complex numbers. The field of complex numbers. Okay, so this is simply a definition. So the proof, as I said, I will not give the computational details of everything, because this is something, it's much better for you to check this yourself. So one checks by direct computations that all the field axioms are satisfied, so that C satisfies the field axioms. which means, so with addition it has to be in a abelian group, then C star with multiplication should be in a abelian group, and distributivity holds, and this is also like distributivity, for example, is something you can really check just using these formulas. This is really just writing things down and seeing that they coincide. So I really recommend to take a sheet of paper and just write this down, maybe pause the video at this point and check. This is not nothing too complicated. Okay, so we check the field axioms, and it's also easy to see that these additive inverses have this formula, so that minus x plus iy is minus x minus plus I times minus y. So this is very simple. I just write this here. This is left as an exercise for you. Okay, the only a bit more complicated part is the formula for this multiplicative inverses, and we can also check this by a direct computation, which I will carry out here. So we check the formula for x plus I1 to the minus 1 via a direct computation. And I will do so after erasing the blackboard. Okay, we have to check that the formula I gave for the inverses are indeed inverses of the elements I claimed, which means I have to show that for some x plus iy in C star, the product with x over x squared plus y squared plus I times minus y x squared plus y squared, that this is indeed equal to 1, the neutral element of the multiplication. And of course the other way around, the other multiplication. And this is something we want to check directly using the definition of the multiplication. So first of all, the first part was that we have the product of the first two entries here minus the product of the second two entries here. So this means we first have this product, which is x squared divided by x squared plus y squared, minus y times this, and we have two minus signs, so we get a plus sign, plus y squared over y squared, x squared plus y squared. And we already see that these two add up to just 1, so this is just 1. Okay, and we get for the I term, this will be called the imaginary part of the number, the product, the mixed entry, so the product of the first entry here with the second here, and add to this the second here times the first here. So first we get minus xy over x squared plus y squared, plus this multiplied with this, which is plus xy over x squared plus y squared. So we see this adds up to 0. So what we get is 1 plus I times 0, and this is nothing but the neutral element of the multiplication, which we wanted. So just using the multiplication rules, this shows that this is indeed the inverse in this direction, and the other multiplication, so we need to show the other way around. So analogously, one shows, it's the same computation, one shows that x plus iy times x, the other way around, that x over x squared plus y squared plus I times minus y over x squared plus y squared times x plus iy is 1. And so this shows then that this, because of uniqueness of inverses, the inverse of x plus x plus iy minus 1 is precisely x squared, x by x squared over x squared plus y squared plus I times minus y over x squared plus y squared. This for all x plus iy in C star. Okay, splendid. We have shown that we have these inverses here, and this kind of, as I said, the rest of the computations can be easily checked, so I will not do them. So this shows that we really have this formula. So now we have really found a field, so an interesting field so far. We don't know much about this at the moment, but this will change. Namely, let me collect two remarks into one. Remark 167. First of all, one checks that the real numbers are indeed contained in these complex numbers. Namely, if we restrict So the restriction of plus and dot, so of addition and multiplication, to the following set. We just take x plus I times 0. So we just take those complex numbers for which this I is multiplied with a 0, and x in R. This really corresponds to addition and multiplication in R. So this simply means that we have to kind of treat the first, this x that is here, so the sum is really the sum of these, of the real entries here, and the product will just be the usual product. This basically follows immediately if you check the definition of addition and multiplication. Correspond to addition and multiplication on the real numbers. And so this is why we can see the real numbers, and this is what we always do, as a subset of the complex numbers actually. So we identify x in R always with x plus I times 0 in C, and then can view R as a subset of C. And this is now something, it's a bit sloppy here when I say that just these restrictions correspond. What this actually means that technically, if you want the precise mathematical terminology, I would say that R is a subfield of C. So let me just, I won't introduce subfields here, but for those of you interested who want to read up, this is the notion. So R is a subfield of C. So indeed, we can view C as an extension of the real numbers. And this extension has an interesting property. And this is now where this funny I has an interesting meaning. Also, first of all, sorry, just terminology. We call the element 1 plus I times 1, I times 0 equal to 1. So the neutral element, also the real unit of C. It's just a different name. And we call the element I, by which I just denote 0 plus I times 1, the imaginary unit. Or just imaginary number. No, not really. The imaginary unit, sorry. The imaginary unit of C. So this element I. And this element I has an interesting property, which is kind of where its relevance is coming from. Namely, if we take I squared, so 0 plus I times 1 times 0 plus I times 1. If we look at the definition of the multiplication, we get that, so the first entry is the 0 times 0 minus 1 times 1, so we get minus 1 plus I times, and then we have to take the mixed entries, 0 times 1 plus 1 times 0, so there's nothing. And this is simply minus 1. So this is the point here. Now this field contains an element which, in terms of its multiplication, squares to minus 1. And this is what we didn't have in ordered fields or in the real numbers before. So here we really get something new, so this is really a new ingredient. And this shows that, for example, if we have this, I had this equation in the beginning, which I know is not on the blackboard anymore, this equation x squared is equal to minus 1. This didn't have a solution in R. But now in C, it has a solution, namely this number I. We see that I squared is equal to minus 1, so this fits the equation. And in the same way, we can then find many solutions of many equations, and you will see some exercises on this in the exercise sheets. You will get to do a few computations with this yourself and really see how nice these numbers then behave or what properties they have. Okay, so this is kind of the idea or the reason for the real numbers being so nice, and I will make this nice property precise in the end of the section. But first of all, I want to introduce some more formalism and some more computations, just elementary stuff about the complex numbers that you really need kind of to work with them. Okay, first of all, let z, usually complex numbers are written as z if you don't want to write every time x plus iy or something. So z equal to x plus iy, let this be a complex number. Then we define the following. The number z bar, so with a bar on top of it, this is defined as, now this is x plus minus xy, and we define this as x minus iy. So just to be precise, this is x plus I times minus y, if you want to be 100% elementary with the notation. So this element in C is called the complex conjugate of Z. And this bar, so this kind of inverting the sign of the part behind the I, complex conjugate of Z. This is called complex conjugation, this procedure. Okay, and now finally I have a word for saying this part behind the I. It's a nice terminology, namely we define numbers, define re of Z and im of Z. These are now real numbers. This is important because some people really mess things up here. These are real numbers which are defined by re of Z is the number x, so everything here which is kind of in the original real numbers, and the imaginary part im of Z is defined to be y, so everything that's behind the x, behind the I, sorry. And yeah, I just said it, so re of Z is called the real part of Z. And im Z, the imaginary part of Z. So, and just a simple remark on the complex conjugation. So, remark 169. So we have seen C, we interpreted this as a version of R2, so of the complex plane, and there's also, of the Euclidean plane, sorry. And there's now this way of kind of viewing C as the plane too, so we identify C with R2 again. And if we take a look at how we viewed it as R2, it was just this real part and the imaginary part that were the coordinates of this point. So we can always write C in some coordinate system here as the plane, where this coordinate here is the real part of Z, and this is the imaginary part of Z. This is what we will do frequently. So if we now have a point somewhere in here that say this is our number Z, or some point that's called Z0, just to say that this is a general for Z. So we have point Z0, which is, this has this real part and this imaginary part here. So if we take a look at the complex conjugate, where is this now in our coordinate system, we just see that we flip the sign of the imaginary part, so of the second component. So which means if this is Z0, we just get, so if this is im of Z0, we take a look at the minus the same part, so minus im Z0, and our point, the conjugate point, is just here. So this would be Z0 bar. The real part doesn't change, we just flip the sign of the part. So this is reflection along the x-axis. And this is something I just want to notice, geometrically, viewing C as R2, viewing C as R2. The conjugate, so Z bar is obtained from Z by reflection, reflection, this is the way to write this, reflection along the x-axis, so the first axis of the coordinate system. Okay, this is what the geometry behind this is. Okay, with this new terminology, with conjugates, real part, imaginary part, I want to collect some properties of complex numbers. And I will not prove the following theorem because the proofs are really elementary, and this is almost, immediately visible. Okay, let Z and W be complex numbers. Then the following properties hold. First of all, if I take Z plus W and take the conjugate of the sum of this new element, this is nothing but the sum of the two conjugates. And this almost follows directly from the definition of the complex addition, because it's just adding imaginary parts up, and so, yeah, reflecting the sign of the sum is reflecting is the sum of the reflections here. So this is, yeah, easy, very easy to see. Then also, and this is not that easy to see, the conjugate of z times w is the same as the product of the two conjugates. So the conjugation behaves nicely in C. This is something I would also, if you really want to understand things, check this yourself. Take the multiplication formula, and this is really writing things down. This is nothing very fancy. It's really elementary. You just take the formulas and see what happens if you write down both sides, and then you will see that they easily see that they coincide. Okay, then B. This is even easier. If I conjugate twice, so if I first conjugate and conjugate again, z bar bar, yeah, what happens is we reflect twice and we get back to the original point. So it's just we flip the sign twice of the imaginary part, and minus times minus is plus. So the double conjugate is nothing but z itself. Very easy. Then what you can see from the formula also quite directly, if we add z to its conjugate, the real part stays the same, so we get twice the real part, and here we get the imaginary part, here we get minus the imaginary part, so it vanishes. This means that this is nothing but 2 twice the real part of z. Okay, same thing if we do z minus z bar. What happens? We get so the real parts are the same, so we subtract the real part from itself, so it vanishes. And for the imaginary parts, here we have y, here we have minus y as the imaginary part, but here we have another minus. So we get twice the imaginary part, and since the imaginary part is defined as this real term that comes behind the I, this is 2i times imaginary part of z. Okay, another thing that's very easy to see, if z is equal to z conjugate, the imaginary part must be equal to minus the imaginary part. So, yeah, of course, this is simply the case if the imaginary part is 0, and this was, by definition, our real numbers. So this holds if and only if it's in the real numbers. Okay, and finally, also something you have to just can check. If, yeah, okay, no, sorry, we need some more notation. If we write z as x plus I y, then, and this is also something that follows directly from the computation, from the definition of multiplication. If I take the product of z and its conjugate, this is what we haven't checked yet here, we have the sums but not the product. If I take the product of z and z bar, this is nothing but I squared plus y squared. Okay, which is a nice little formula. Okay, so these things I ask you to check yourself, and yeah, now erase the blackboard and we see some further constructions with complex numbers. We have previously defined the absolute value for ordered fields, where we use the ordering and the notion of positive and negative numbers, and yeah, introduce this notion of absolute value with this. In the complex numbers, we don't have this construction because we don't have an ordering here. But it turns out we can still define an absolute value in the sense that we have a map which behaves similar to the absolute value as for ordered fields, for example, in the real numbers. Namely, the following. Definition 171, the absolute value of an element z in C, z, I will give the real part and imaginary part names. Z is x plus I y in C. And this is simply the number z bar, so z in absolute values, in vertical dashes again. This is defined as the square root of x squared plus y squared. So the sum of the squares of real and imaginary part of the number. And as we learned in the previous theorem, this can also be very shortly written as the square root of z times z bar, because this is just this number here. Right? So this is a nice way of writing this without real and imaginary part, but this is the definition of the absolute value. And before we see its properties, we can just see some motivation. So why on earth should we consider this number? And it turns out it makes sense. Namely, first of all, if we again identify C2 with the Euclidean plane, so let me draw some diagram. Let's just take one quadrant here. So this is the real part of Z, this is the imaginary part here. So if I have some point Z, the square root of sum of x squared plus y squared, so this would be x, this would be y. And if you take a look at this, you probably already have, everyone of you has seen kind of vector addition in R2 and so on. This value here, the square root of this, is just the length of this vector. If we see this as kind of as R2, so with the Euclidean matrix and so on. So this means the length of this vector, this is what we define as the absolute value here. So like you can see that this has the same length. If you haven't seen this construction yet, if we draw a line here, this is a rectangular diagram, and so the length of this is by what do you pronounce them in English? Pythagorean theorem, okay, you know what I mean? The length of this is the square root of the squares of these two lengths. So, antique Greek geometry. But this just means this number is really the length of this as a vector in R2. So, identifying this with the Euclidean plane, Z, so the absolute value of Z is the length of Z as a vector in R2. So, and this is why this number is indeed interesting. Secondly, we have the real numbers in C as we've seen. So if x is now a real number, which we view as a subset of C, then this new absolute value, this would mean, so this would be the absolute value of x plus I times 0. This is then nothing but the square root of x squared. But this is again the old absolute value. This is, so the only non-negative solution of this equation is the real absolute value of x. So now we have two different notations for the same thing, because it turns out here that it is the same thing. Maybe let's erase this. So this is indeed coincides with the old absolute value, which coincides with the old absolute value. It's not that old, it's just from last week's lectures, but anyway, with the old absolute value. So we really have an extension of our concept of absolute value that we had before to this field where we have no ordering on C. Okay, and another reason why we are kind of allowed to name this an absolute value is that it shares similar properties with the old absolute value that we know. Namely, we collect some properties of this absolute value. For all Z, W in C, we have the following. A, first of all, the absolute value of Z is always non-negative. So the absolute value is now a real number. This is maybe something, just keep it here. So this is really an element of R now. The absolute value of a number is always an element of R. It is always non-negative, and this is clear since it's defined as a square root, and square root are always non-negative. Okay, so this is true, and it also holds, and this is also easy to see, Z bar is equal to 0. The absolute value of Z is equal to 0 if and only if Z itself is 0. I mean, this also follows directly from the formulas. So B, and this is something also quite obvious, the absolute value of Z conjugate, of Z bar, is the same as the absolute value of Z itself. Remember that only the imaginary part changes its sign, but since there's only a square in here, minus squares to plus, so this doesn't matter for us. It's also easy to see. C, the absolute value of the real part of Z. So this is now a real number. This is smaller than or equal to the absolute value of Z, and This also makes sense because the real part in this formula here would only be x, so we would just have the square root of x squared, which is obviously less than or equal to the square root of x squared plus y squared. So there's nothing much to show. Same holds for the imaginary part. The value of the absolute value of the imaginary part is at most the absolute value of z itself. Again, this is also a real number. Then D, so now we take a look at the behavior with respect to products and sums. The absolute value of a product of two numbers is the product of the two absolute values. This is not entirely obvious, and I will prove this in a second. And we have the infamous triangle inequality. The absolute value of a sum of the sum of z and w is smaller than or equal to the sum of the two absolute values. And now I can tell you why it's called triangle inequality, because this is again motivated by what we get when we take a look in the on C as the Euclidean plane. So let's write just one quadrant again for simplicity. So this is C. And if we now have two different complex numbers, so let's say we have let's call this here z, and we have some number w, and assume we have seen that the addition in the complex numbers is just addition of the components. So this is vector addition in R2. So if this vector here, if we view this as the vector z and add the vector w, this would be maybe something like this. Let's say this is w, and we add this vector. This means just putting these arrows behind each other. So the point z plus w would be this one, this corresponding to this vector here. And so, since the absolute value is the length of these vectors, this just says that the length of this one here, this vector here in the triangle, is at most the sum of these two, which is in this sense quite obvious. So if we go to some point, this basically says if we take a detour through some other point, the road won't be shorter. So this is really the shortest connection here. Right? So this is why triangle. So this one side is, the length of the one side is then bounded from above by the sum of these two sides. So this is how intuitively you can really understand this triangle inequality. Okay. Yep. So, proof. So as I said, parts A, B, and C follow immediately. This is really easy to see. Immediately. Then part D, so the products here. So by theorem 170a, that was the result of a complex conjugation. I will see in a second where we do this. So let's take z times w as an absolute value. And now, since we know this is non-negative, and we want to show that this is the product of the two absolute values, we can do the same for the squares. Because if it's non-negative, so the squares, they have a unique solution unique non-negative solution. So if the squares here coincide, then the terms will coincide as well. So I have said that we can now use this fancy formula here, so that we can write this as the square root of z times z bar. And this we want to apply here. So since we square, there's no root involved. This would then be z times w times the conjugate of z times w. And this is now theorem 170a, which said that the conjugate of a product is the product of the conjugates. So this is the same as z times w times z bar times w bar. Notice that I'm also not using any parentheses here because we're in a field and so the ordering doesn't matter, and so we can just leave out parentheses at all. And it turns out that since the field the multiplication is abelian, so we can just flip the order of the middle two terms. And this means this is the same as z times z bar times w bar. Okay, but if we now take a look at these guys here, so we can view this, like if we want to put parentheses in here, we can view it like this. And now we have, again, relations to the absolute value. Namely, taking a look at this formula again, the first part is nothing but z squared and the value, absolute value of z squared times the absolute value of w squared. And since, as I said, since the two absolute values are non-negative, this implies that the absolute value of z times w is the product of the two absolute values without the squares. Okay. Yeah, it remains to show the triangle inequality, and this is also a nice little computation. There we also need theorem 170, and namely we need to see how conjugation behaves with respect to products. By theorem 170. So we do the same with the squares, because we know that if these numbers are non-negative, if the square of the left-hand side is smaller than the square of the right-hand side, then by the axioms for ordered fields, it follows that without the squares, we will also have this inequality, just by non-negative terms. Okay, I can't write in a straight line anymore, I'm sorry. Okay, so what we need to do is to take the left-hand side, z plus w, and the absolute value of this, square this, and then see where we end up. So, this is by definition z plus w. Now we have to put the parentheses because of the dot and the plus interacting, times the conjugate of this sum. But this is now where theorem 170 kicks in. This is nothing but the sum of, so this here is nothing but the sum of the two conjugates. So this is the same as z plus w times z bar plus w bar. And now we can just use distributivity and really multiply everything out. And then we can see that kind of this is the same as this times this, plus this times this, plus this times this, and so on. So if we multiply this out, or maybe I can continue here since I've got some space left. This is the same as z times z bar plus z times w bar plus w times z bar, which I write the other way around because we're abelian here. Z bar times w plus w bar. Okay, so first of all, this is the same as the absolute value of z squared. This is the same as the absolute value of w squared. And now I can use a trick. Namely, here we have z w bar, and if we take a look at this summand, we can now use the trick that double conjugation is no conjugation, namely w is the same as w bar bar. And if we then use again the compatibility with products, it turns out that this is indeed the same as z times w bar and then bar over the whole thing. Okay, why on earth do we need this? If we now take a look at these two middle terms here, this is a number plus its number bar. And there we've already seen in theorem 170 that this has a nice property, because if you just take a look at the number here, this is nothing but twice the real part of this. So this is z bar squared plus twice the real part of z w bar plus the absolute value of w squared. Okay, we're not there yet, but we're getting somewhere. First of all, this is a real number, and for a real number we know that always a number is bounded from above by its absolute value. So this is smaller than absolute value of z squared plus twice the absolute value of the real part of z w bar plus the absolute value of w squared. Okay, but then we've seen, no, it's not, it was part C we can directly use here, because we can now estimate the real part by the value of the number itself. So we get rid of this real thing there in the middle, and it turns out that this is then bounded from above by z bar squared plus twice absolute value of z w bar plus absolute value of w squared. Okay, now here we can now again use the compatibility with products. So this is the same as z absolute value of z squared plus 2 absolute value of z times absolute value of w bar plus absolute value of w squared. And now probably some of you can see where this is going. Here we can now use part B. So conjugation doesn't matter inside the absolute value. This is z, absolute value of z squared plus twice absolute value of z times absolute value of w plus absolute value of w squared. And now it looks nice, because this is just by this binomische Formel, as they call it in German. So this is just the square of absolute value of z plus absolute value of w. Whoops. So this was a long chain of inequalities. So we started off here and then but we only estimated to the one direction. This is important when you follow inequalities, just as a general thing. It only gets bigger and bigger and bigger. We're not getting together with, we're not taking some inequality in another direction, then we would be cheating, but now it's still bigger, bigger, bigger. And so if we follow this thing, this then implies that, so we have shown that z plus w, the absolute value squared, is smaller than or equal to this square here. So absolute value of z plus absolute value of w squared. And since all terms are non-negative, so all are non-negative, a bit sloppy, but anyway, this implies that z plus w to the absolute value is smaller than or equal to the sum of the two absolute values. And this is what we wanted to show. This is the triangle inequality, and now we're happy. Okay, let me erase the blackboard. Okay, let me finish off this section by stating two more crucial properties of the complex numbers, and I will only prove one of them, but just to show you what they are doing. First of all, there's one big difference to the real numbers, and I've mentioned this before, but now I will formally prove this. Ah, that's a strange piece of chalk. Wait. Ah. There's a lot of variety in the quality of chalk, but I won't get into a monologue on this now. So, theorem, there exists no total order on the complex numbers. Of course, if we have this ordering on the real numbers, I mean the real numbers we can see as the line now, and there we have this ordering by kind of what's left and what's right. So how can this corresponds to the total order we've studied on R so far, so the unique total order essentially, but there exists no total order on C. There simply is none. Of course, there's no obvious way. I mean, if we cannot order everything in the complex plane or in the plane, so it's kind of a question of what should be bigger or smaller or something. But we can really prove that there is no such order, so we don't need to search for it. Proof of this, actually not that hard. Suppose we had an ordering. So suppose no total order. Sorry, making C an ordered field, so compatible with the operations, making C an ordered field, so with satisfying these properties. That's the crucial thing here. So suppose C was an ordered field. Oops. Field with respect to some ordering which we again call smaller than or equal to, whatever that should mean. So it's just an abstract order at this point. So then, in particular, since it's the total order, we would have a relation between the number I, so the imaginary unit, and 0. So either would be not either. It would hold that I is bigger than or equal to 0, or that I is smaller than or equal to 0. And for both of these settings, we will now construct a contradiction. So if I was bigger than or equal to 0, then we also know that the third power of I is bigger than or equal to 0 by the properties of ordered fields from theorem 138. Don't know which part of the theorem, I haven't noted that, but we know that powers of non-negative elements are non-negative. So this would hold as well. But I to the 3, this is of course the same as I squared times I. But we have computed before that I squared is minus 1. So this is minus 1 times I, which we write as minus I. So this would mean that minus I was bigger than or equal to 0 as well, since minus I is I to the 3. But this would then imply, because flipping the sign changes the sign of the equation. This is just a general property of ordered fields. So this would imply I is smaller than or equal to 0. But if this holds and this holds, then this would follow, it would follow that I is equal to 0, which is obviously wrong. So this is a contradiction. Contradiction. So, okay. So this cannot be true. So what about the other situation? So if I is smaller than or equal to 0, then similar situation, then minus I is non-negative. Again, minus sign flips the equation, the inequality. So, but then, same as before, the third power of this, minus I to the 3, would also be non-negative, but, and now it's a similar computation, minus I to the 3. This is minus I times 1, and since the multiplication here is commutative, this is minus 1 to the 3 times I to the 3. And we've seen I to 3 is minus I, is minus I. And this here, minus 1 to the 3 is easily seen to be minus 1. So this is minus 1 times minus I, yes, which is I. Minus times minus gives plus by this general property of ordered fields. So this would mean I is bigger than or equal to 0, but since we've assumed that it's smaller than, we would again get the same contradiction. Namely, we would get that I is equal to 0, and this is again a contradiction. So there is no total, hence, maybe, it's not that important, but let me let this final sentence. Hence, there is no such order. Okay, so we don't have to search because there isn't any. So C cannot be ordered. Then I will, now as a final theorem, as a kind of, nice dessert, I give you this theorem that tells us the important thing about solutions of equations, was what I mentioned in the beginning, namely the very famous fundamental theorem of algebra. And very beautiful statement, and I'm not able to prove this now. We need some more prerequisites. I will maybe present a proof later on. Let's see how this course goes. But we need quite some, we need to extend our toolbox first. So we need to do some stuff about this. But I will just give you the statement, which is easy to understand. Namely, the idea is if we have some polynomial equation in the complex numbers. So for all n in n and numbers which will be coefficients a0, a1 to an minus 1 in C, the equation z to the power of n plus an minus 1 times z to the n minus 1 plus and so on. So descending powers here plus in the end a1 times z plus a0 equal to 0. So this is the general form of a polynomial equations. Just put a leading coefficient to 1 because this doesn't matter. So this equation here always has a solution in C. In C. So this always has a solution in Z in the complex numbers. And as we've seen before, this is not necessarily the case because in the real numbers, because one example was this x squared equal to minus 1, which would correspond to the polynomial equation here, x squared plus 1 equal to 0. And so here we see in the complex numbers, we can take all possible polynomial equations here, all equations of this form, we always find solutions. This is, the property is also called C is algebraically closed, but this is just terminology. But this is a really useful property of these complex numbers, and this is kind of one of the main reasons why these are so important, popping up everywhere. Okay, so we cannot prove it at this point. I just wanted to present it to you because it's so beautiful, and because this is kind of one of the main motivation to study it. So we cannot prove it, parenthesis, yet. Maybe we will do later, but we'll see. But this is the crucial property of the complex numbers. And as you will see, they will pop up in physics quite frequently, and there's a lot of, they're much more natural than you might think now, because now it looks quite like an artificial, arbitrary construction, but it turns out it really isn't. It really has some very natural, nice properties, We will see more of them later, but this so far completes the first chapter, and now in the next chapter we will talk about sequences, which kind of is the first glimpse into single variable calculus, what the main objective of this course is at. Okay, so I hope you enjoyed, or maybe understood the first chapter quite well, and I hope you had a good time watching these videos, and we'll see you in chapter 2.